Hi, this is Math 8, Unit 7, Lesson 11. Today we're looking at representing small numbers on the number line. So sorry first off for any background noise. I'm at a college in Washington right now, waiting for the band to perform. And there's people will be coming in here and band playing soon, but try to get the videos done for you guys. So it says, first of all, let's visualize small numbers on the number line using powers of 10. So small numbers. It says Kieran drew this number line. We have 1 times 10 to the negative fourth, 2 times 10 to the negative fourth, and so on, all the way to the negative fifth there. Andre said that doesn't look right to me. Explain why Kieran is correct, or explain how he can fix the number line. So we're not quite sure. There's an or question here. Is this right or is this wrong? So when you think about this, if this is 0, and this was to continue on this way for a long time, eventually you'd get to the number 1, right? So you'd have 1 over here. So the further you go this way, the smaller the number is going to be. The more you go this way, the larger the number is going to be. Okay? Because at this point you're talking about numbers between 0 and 1. You're talking about fractions like 1/10 or 1/100. Those are the kind of numbers that you would have in between these spaces here. So when we take a look at this, if you were to do 9 times 10 to the negative fourth, right, that's going to be 1 over, and then we have 1, 2, 3, right, 4, so 1 in 10,000, something like that, and 9, so 9 10,000ths, and so as a decimal this would look like 0.0, there's 10, 100, 1,000, 10,000. So this number right here is actually, right, 9 or 99 10,000ths. That's how you say that there. Sorry, can't think so much this morning. All right, so when you go to this number here, this one becomes, the problem with this one is that is actually smaller, right? So the fifth is actually smaller than to the negative fourth. So this number needs to actually change to be 10 to the negative third power. Now the reason for that is, again, if we think about it, this should be 10, if we take this one here, this becomes 10 times 10 to the first times 10 to the negative fourth. If we're following the pattern, right? 9 times 10 to the negative fourth. If you follow the pattern, 10 times to the first times 10 to the negative 1 is same base, add the exponents. What is 1 minus 4? 1 minus 4 becomes a negative 3. So this value here should be 10 to the negative third is what the value should be. So that's what's going to happen because we're getting actually larger this direction. So larger is going to be 10 to the negative third would be 1, 1, 2, 3, right? So here, something like that, which is a larger number than what you have over there. So when you're dealing with smaller numbers, just keep in mind that the more you go to the left, the smaller that number is going to be, right? This over here could be something like 1 to the 1,000,000th kind of thing, whereas over here, we could have a 1/10th, and that's going to be larger. So a little different way of thinking on this one. Let's take a look at some more examples. All right, first thing here, it says label the tick marks on the number line. All right, so what we did before, we know that this value here is actually 10 to the first times 10 to the what? Negative, we're going to say right here, 10 to the negative 6. Okay, so yeah, so this is going to be 10 to the first times 10 to the negative 6, meaning that right here I'd have 9 times 10 to the negative 6. And again, this works because 1 plus a negative 6 gives you 5, right? This one's actually correct this time. In my head I had to pause there because I was thinking it's wrong, but this one was wrong. So this becomes 8 times 10 to the negative 6. Here we have 7 times 10 to the negative 6, 6 times 10 to the negative 6, 5 times 10 to the negative 6, 4 times 10 to the negative 6, 3 times 10 to the negative 6, 2 times 10 to the negative 6, and finally 1 times 10 to the negative 6. So we're going to now plot the following numbers on the number line. So for 6 times 10 to the negative 6 for point A, that's going to be right here at this point. No problem. Got it. For 6 times 10 to the negative 7th, well, gotta think about this here. I want to go ahead and make this number 1, think about it, I want to make it 1 more. I want to make that a negative 6, right? So to make it 1 more, when I make it more, then I need to move the decimal to the left. So I move the decimal to the left, I increase the size of the exponent. So I end up with 0.6 times 10 to the negative 6. So to make it more, again, negative 6 is greater than negative 7, so that's increasing by 1 of my base 10 values. I'm going to move the decimals to the left there. So where's 0.6 going to be? It's going to be somewhere over here. So there's where B is going to be. Here, same idea, I want to increase this, right? So I want to increase it by 1, so move the decimal place over by 1 there. So I'm going to put 2.9 times 10 to the negative 6. So 2.9 is going to be right about there, and we'll call that point C. And then here, I actually want to decrease because I have negative 5, I want to go down. So because I want to decrease it, I'm going to move the decimal to the right. So I have 7 times 10 to the negative 6, which will be located right about there for point D. So we plotted that out there. So which is larger, 29 times 10 to the negative 7 or 6 times 10 to the negative 6? We want to get these in the same base 10. So you can go up or down, whatever way you want. Okay, in this case here, let's make this, because negative 7, let's go ahead and increase it. So we're going to go up. So when we go up, we go to the left. So this becomes 2.9 times 10 to the negative 6. Now we can compare because we have the same base 10. So 2.9 is going to be less than 6 times 10 to the negative 6. So which one is going to be larger? Oops, sorry. Because we're dealing with negative numbers there. Sorry about that. Back it up, back it up. I wasn't thinking about negative 6. Okay, so don't do what I did. So what does this mean? Remember, because these are going to be like decimal numbers, right? So fractions. In this case here, the larger one is going to be the one that's closer to 1, not closer to 0. So just be careful as you think about this here. So in our case, you're moving the zeros around. We're still going to say this is bigger because it's 6, which is greater than 2.9. So we're still going to be okay there, and that's going to be about 2 times larger. So sorry, I started to confuse myself there. I thought I was catching myself in the air, but I was okay. Good thing. All right, here we have 7 times 10 to the negative 8, or 3 times 10 to the negative 9. Again, whichever way you want to do. If I want to go to negative 8, I can change this to negative 8. So I'm going to be actually, in that case there, going up, because negative 8 is greater than negative 9. When I go up, I move this to the left. So I have 0.3 times 10 to the negative 8. And I'm comparing that to 7 times 10 to the negative 8. So which one's going to be greater? In this case here, we would say this is going to be greater than that one right there. And so we're set to go. How much greater is it? Well, it's going to be a lot greater. In this case here, 3 times about 20 times greater, or actually more than that, about 23. If you wanted to get a number you could work with, all right, let's just say we want to make it a regular 3. So if I move that to this direction, I could call this 3 times 10 to the negative 9th. I'm going to the right, so I make it smaller. And I can make this go to the right, make that a 70 times 10 to the negative 9. So it helps you look at whole numbers and compare 70 to 3. The difference between these two, right, if you just did some division there, my answer key says it's about 20 times. Well, 3 times 20 is 60, so it's actually more than 20. And in reality, if I did 23 times 3, you end up with 69. So I would say personally about 23 times greater is what you'd have here from one number to the next. Okay. Let's take a look at the next page, looking at what's called the atomic scale. On the atomic scale, it says the radius of an electron is about a crazy long number, a lot of zeros and a 3. Write this number as a multiple of a power of 10. Again, this is our goal here, is to write these things a little bit nicer. So we can see if we stop right about here, okay, and we kind of count back this way to the decimal, let's see what we have here. We have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 spaces that I want to get behind the decimal there. That's 13 right there. So to write this as a multiple power of 10, we would say that I have 3, that's my number, times 10 to the negative 13. Okay? That's how many spaces are going to be coming after, or I mean, how many the book calls it how many decimals are going to come after the decimal place. So I mean, it's really how many place values are going to come after. It's 13 there. All right, decide what power of 10 to put on the right side of this number line and label it. Label each tick mark as multiple power of 10 and then plot the radius of electrons. So we're going to try to plot this down here. So if this is negative 13, we know that our base is, if we're going to have 1 times 10 to the negative 13 and 2 times 10 to the negative 13 and 3 times 10 to the negative 13, we know eventually we're going to plot it right there. But what has to happen with this value there? Remember that if that's going to be a negative 13, then what I have is I have 10 to the first times some number to negative 13th. When I combine these, 1 plus a negative 13 equals what? Equals a negative 12. So what needs to go in that box should be 10 to the negative 12, because it's actually getting larger, right? Larger as we go in that direction there. So that's what would go in that space. Let's do another one. Just good practice this again and again. So again, we're looking at a crazy long number once again, right? Here's 17 grams, but it's not 17. It's all this zeros. Write this as a multiple power of 10. So to do this, let's go ahead for now and let's put it as 17. And we could do 17 for now. That's okay. I'm going to do 17 for now just so we're in a good spot there. Okay. And when we do 17, we're going to take a look and say, well, if this is where I'm at, how many spaces does it take to get to there? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, and 25. So that's 17 times 10 to the negative 25th power to get all the way to that space right there. Now, because I'm looking over here at a tick line again going from 0 to 10, I don't want to have a number like 17. So let's move this over to the left. Moving to the left means I'm making it, to the left means I'm making it larger. And what's larger than negative 25? That would be 10 to the negative 24th power. All right, so on my tick marks here, I know I'm going to have 1 times 10 to the negative 24th. And over here, I'll have 2 times 10 to the negative 24th. And 1.7 is going to land somewhere about here. That's where 1.7 is going to be, between 1 and 2. So now let's come back to my side over here. This is going to be 10 times 10 to the negative 24th, 10 to the first times the negative 24th. When I combine those exponents together, what value do I get right there in that box? It's 1 minus 24, so I should have 10 to the negative 23rd. Okay, so do we plot it? Yes, we did. We plotted it right there. And that's the idea. So you can see that by using these powers of 10s, we get a lot better, it's a lot easier to see what these numbers are going to be. It's really difficult to use all those zeros and figure out where something should be. So just keep that in mind there. All right, let's look at the next one. Again, another example, a lot of similar things here. It says point A on the zoomed in line describes the wavelength of certain X-ray in meters. So again, we can see we have 10 to the negative 12th power all the way through to 10 to the negative 11th right there. We're looking at what's happening between the 6 and the 7. Okay, all those points there. So again, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which tells me this is going to be 6.1 times 10 to the negative 12. All the way over here to, here's 2, 3, 4, 5. Let's make this 6.5 times 10 to the negative 12. And it goes on and so forth throughout the whole thing. So what is the wavelength of X-rays as a multiple of power of 10? So we're looking at right here, that point A, which is between 6 and 7, and using a little more decimal notation, that would be 6.1 times 10 to the negative 12. All right? Now to write that as a decimal power, this is going to be a little bit annoying, isn't it? Here's the way I write this as a decimal. Okay, I'm going to write my 61 first of all. Okay, maybe if you wanted to, maybe it helps you out. Well, it's okay. We're going to do 61 because that's the number I'm looking at there, right? So there's 61. And then when I look at this, what happens is I know that I have the decimal starting right here, and I'm going to need to go this way 12 spaces is the idea for my decimal point. Okay, so So this 6 starts as my 1. Okay, 9. So that's 1. And we have 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the decimal, it looks something like that. Okay? So we have 12 decimal spots between the 6 and the 1, all the way to this decimal right there. So that's your number, what it looks like. If you want to look at groups of 3, here's a group of 3, here's a group of 3, a group of 3, and then a group of 1, 2, 3. That's the 12 to get there. And that's the idea. Cool. So in summary, if we were to take a number like 2 times 10 to the negative 6, we can see that where that would go on a number line looking something like this. So we can plot that. We have to find 2 powers of 10 that lies between there and there. So the key thing we did today also was this part to say what should that number be right there. And again, that's 10 to the first times 10 to the negative 6. When you combine those, that gets you to negative 5th. So remember, we're getting larger as we move to the right, which means that the negative value is going to be increasing. Looks like it's decreasing absolute value wise, but it's not. All right. So the power of 10 on the right side of the number is always greater. So the power of 10 on the right side is always greater than the power on the left. This is true for positive or negative powers of 10. Okay, so that's your idea. Let's go ahead and take a look then at your homework for tonight. So press pause, get some homework going, and let's see how you do. All right, select all the expressions that are equal to 4 times 10 to the negative third power. All right, well, let's take a look at what this number actually is to start with. 10 to the negative third power, that's going to be 1 over, and we have 1 with 3 zeros, 1, 2, 3. And because we're talking about a 4, right, you end up with 4 of those. So we end up with 4 over 1, 2, 3. Right? As a decimal, this is going to be 4 thousandths. So here is our tenths, hundreds, and thousands. So that's the number we're talking about right there. So a way of writing this as a fraction could be there. Writing it as a decimal could be there. Writing it in this notation looks like that. So now when we take a look at these things here, here I have 4 times 1 times 1 times 1, which is going to be 4. And then 10 times 10 is 100. 100 times 10 is 1,000. So we're sitting at 1,000, and that's going to be okay, right? That's the same idea, no problem. I could also look at it saying as this is 4, which is that's just there, and then 10 to the negative third. 10 to the negative third is the same as doing, right? This is 10 to the negative 1, 10 to the negative 1, and 10 to the negative 1. Because the bases are the same, I can combine those, and negative 1 plus negative 1 plus negative 1 still equals a negative 3. So this one's going to be good. Here, this is a negative 10 times negative 10, which is 100, and 100 times a negative 10 is a negative 1,000, and negative 1,000 times 4 is simply negative 4,000. So that number in itself is not the same as 4 thousandths. So that's not going to work. Here, we have 4. Right, that's our 4 there. And when we look at this, what is this as a value? This is going to be 10 to the negative what? How many spaces are we talking about here? We're talking about, in this case here, this is the thousandths. So to get to 1,000th, that's going to be how many zeros? 3 zeros are going to be with 1,000th, right? So how many, you could look at how many are for the decimal if you wanted to, right? So 1, 2, 3. That's what it looks like, and that matches what we're aiming for. On this one, we can see that it's going to go out too far. This one is designed to see if you get tripped up and say, oh, it's going to be 3 zeros as opposed to 4 spaces behind the decimal. So that's not going to work. This is actually 4 times 10 to the negative 4th power. On this one what they've done is they've combined that and actually multiplied it out, right? This is 4 in the thousandths place. So it actually is going to be just fine. That's a good one. And this one here matches which one? It matches this one, which you already know is wrong. So we're going to say no to this one as well. Number 2, write each expression as a multiple of a power of 10. Cool, no problem. So let's do this one first. We have 4, awesome, times 10, and then how many spaces are behind the decimal? 1, 2, so the negative 2 power. You want to think about it like this. This is tenths, and this is hundredths, and hundredths is like this. So again, how many zeros there? Negative 2, because we're below or the denominator. Here, let's do the same thing. I'm going to go ahead and break it up right there, though. All right, just to get a pattern here. So I'm going to do 7.2. Now, because it's 7.2, I want to say, in this case here, how many spaces are between the decimal and that place I'm going to break it. In this case, I have 1, 2, so 7.2 times 10 to the negative 2 power. On this next one, we're going to break it up right there. So we're going to do 3.25. And then here, times 10 to the what? Well, how many spaces till I get to that decimal break right there? How many space holders are in that block? 1, 2, 3, 4, 5. So we're going to make that 10 to the negative 5th power. 3 thousandths. Okay, 3 thousandths. So 3 thousandths. I can write it that way. I can also write it as a decimal, 3 thousandths. There's tenths, hundredths, thousandths. Both those work the same. Now, in terms of writing the way you want to write it, let's do the 3. Okay, we'll put our mark right there. It just becomes 3 times 10 to the negative 1, 2, 3, negative 3rd power. 23 hundredths. Okay, 23 hundredths. That's the idea. So if I write this first of all, I could say 23 times 10 to the negative 2, because there's 2 zeros there. I don't like it as 23. I'm going to move this over to the left one. Moving to the left means that's going to have to then increase, right? So we're going to have to add 1 there. So what's going to happen? I'm going to put 2.3 times 10 to the negative 1. All right, so make sure you kind of get used to these little tricks here and do them again and again. All right, 729 thousandths. So 729 thousandths. Again, writing out long way, you might say 729 times 10 to the negative 1, 2, 3, negative 3. But I'm going to move this over 1, 2 spaces. So that becomes 7.29. Now I'm going to add 2 to this now. Okay, adding 2 to the negative 3 becomes what? 10 to the negative 1 again. Okay, so I got that by moving it over 2 spaces. Now I'm adding 2 to that exponent there. And then that last one here, 41 millionths. 41 millionths, that's exciting. So 41 over a million. So that's going to be 1, 2, 3, 4, 5, 6, right? That's kind of like a lot of numbers there. So that's going to be 41 times 10 to the negative 6, because there are 6 zeros there, because I'm doing millions. I don't want to leave it like that, so I'm going to move that over 1 space, which means I'm going to add 1 to that one. So this becomes 4.1 times 10 to the negative 5th power. And that's the idea. All right, got the idea there? Very cool. All right, the next one says the family sets out on a road trip to visit their cousins. They travel at a steady rate. The graph shows the distance remaining to their cousin's house for each hour of the trip. Let's get this graph and see what it looks like. Looks like something like that. All right. So I'm going to zoom out so we can see the whole page here, or most of it I hope. First question, how fast are they traveling? The rate that they're traveling, the fast, that's going to be your rate, is going to be that y over x value. So we have to pick a point and say, well, let's go from point to point and see what we want to do. So however you want to do this here, we've got 480. We have another point right here at 420. So it's a difference there. So 480 minus 420 divided by our change in x and y. This is like the y1 or y2 minus y1 kind of thing, however you want to do that there. And we're this over the course of 1 hour. So in 1 hour, we make this nice triangle like this. We're going to be going, in 1 hour, the difference between 480 and 420, so they're doing 60 miles in 1 hour. So in terms of the rate that how they're going and how fast, that'd be 60 miles per hour. Is the slope positive or negative? In this case here, we would say the slope is going to be negative. Now the reason we know that slope is negative would be if we take, we can see a couple things, right? It seems to be decreasing just visually, right? So it's going down, right? That's one thing. So distance y is decreasing with time. So it tells us our slope is negative because we're going down this way. How far is the trip and how long did it take? Well, the length of the trip, or the distance, right? That's going to be our distance. Because this trip has a starting point of 480 and an ending point of 0, the distance is simply 480 miles. Okay, the time it took is going to be indicated by how long it took to go from 0 hours all the way to the end, which is going to be here at 8. So it takes 8 hours to complete that trip. And that's all there is to that one. That's it for today. Have a great one, and we will see you next time.